Let's hop into the second recursion review. So this video will be reviewing exhaustive search. As a refresher, exhaustive search is used to find all possible combinations or permutations given some type of limitation or condition. So exhaustive search uses a slightly more nuanced definition of base and recursive cases. Our base case is a valid answer. So once we have a valid answer, we maybe print it or process it in some way. We also have an implicit base case. So this may not be explicitly written out, but with an implicit base case, we stop recursing because it's impossible to arrive at a valid answer. And for a recursive case, this is where we explore all potential options by changing the parameters we give to recursive calls. And each option requires its own recursive call. Decision trees are a tool we can use to help with visualizing exhaustive search, where it's a diagram that represents a set of choices of an exhaustive search algorithm. And it shows a series of choices or decisions and the potential outcomes. So for this example, this decision tree represents an exhaustive search, which prints out all strings of length 3 containing only 1s, 2s, and 3s. And at each stage, we can either add a 1, a 2, or a 3 to the string we're building up. And this repeats all the way until our string is length 3. Tips for exhaustive search. We almost always want to use a public-private method pair, as it's good convention, and we can tell exactly which public method our private helper method, usually with more parameters, belongs to. Almost all exhaustive search methods will have an if base case and an else if specific recursive case. And this will allow us to handle the implicit base case, where we'll only keep recursing if we can still generate a valid base case answer. Almost all exhaustive search problems can be solved by identifying a so far primitive, usually a string, that we build up with every recursive call, and a counts value that we track or update, and that tells us when to stop recursing. So for using our previous decision tree, the so far we're using is we're building up a string of digits. And the count is the length of that string. We'll stop recursing once the length of that string that we built up is equal to 3. So my tip to you is to draw a decision tree if you're having trouble finding where to start. A lot of the times drawing out a simple decision tree for a small example can help build the intuition for a problem where maybe you weren't able to see it right away. Let's practice. The problem we'll be doing is print numbers. We're tasked with writing a recursive method, print numbers, that takes in integers a, b, c, and d, and prints all of those integers, or all combinations of those integers, with b number of a's and d number of c's on separate lines. So if you're given a method called print numbers of 1, 2, 3, 4, we want to print every combination of 2 1s and 4 3s on different lines. And that's what's shown below. Last but not least, if any of the integers are negative, we would want to throw in a legal argument exception. Just something to keep in mind. Let's draw out the decision tree for this method. I want to draw out the decision tree for print numbers of 1, 2, 3, 1, just because it's a smaller example. This would take less time to draw out the entire tree than for a larger example, as well as using a smaller example, it usually is enough to build intuition for a problem. So we want to draw out a decision tree that demonstrates our method and how we would print out all combinations of 2 1s and 1 3s. To start, we have 2 choices we can make of either adding a 1 or choosing a 1 to our string or choosing a 3. And this process of either choosing a 1 or a 3 to add to our string is made at every stage of the decision tree. So in this example, we added 1 to the 1 we chose in the first stage, and this other node represents adding a 3 to the one we chose in the first stage. And this process continues until we hit 3 digits. In this tree, only a select number of 3-digit strings are valid, as they only contain 1 3 and 2 1s, the exact number that's needed. If we were to hit, for example, a 3 3, even though the string is 2, only has a length of 2, the fact that we have more than a single 3 would automatically make this option valid, and we should probably stop recursing, as we'll see when we code this up. Let's try to find our so far and our counts. So as we saw from our decision tree, we were building up a string of digits. So this could be considered our so far. And for the counts we care about the number of letter A's and the number of letter of B's. Once we have the appropriate number of A's and B's, or ones and threes in this example, we should stop recursing. And if we don't have the appropriate number, or if the number of ones and threes we had made it so we can never reach a valid answer, we should stop recursing. So this is our counts. And from here, let's try to derive our base and recursive cases. So our base case is when the number of A's in our string is equal to the desired number of A's, and the number of B's in our string is equal to the desired number of B's. Then we can print. For our implicit base case, when the number of A's in our string was greater than the desired number of A's, or the number of B's in our string was greater than the desired number of B's, we should stop recursing. This is the case where we had a 3-3, right? The client only wants us to print a single 3 in our final string. So the fact that we added more than a single 3 means we should stop recursing, as there's no longer a way to generate a valid string with 2 3s. Finally, for the recursive cases, when the number of A's in our string is less than or equal to the desired number of A's, and the number of B's in our string is less than or equal to the desired number of B's, we should explore all possible options. This means making a recursive call where we add an A to our string that we're building up, and making a recursive call where we're adding a B to the recursive option we're building up. Let's code this up. So I hopped on over to Ed. Right now, I set up a private helper method that we'll use in our public-private pair, as well as wrote in our basic recursive cases. And I gave the private method parameters int a, int num-a, int c, int num-c, and a string subvar. So a and c are the 2 digits we'll use to build our string, and the string that we'll be building is our so far string variable. We also need a way to keep track the number of a's and the number of c's that we've added to our string. So we can do that with adding a num-a and num-c example or parameter. First, let's call our private helper method inside of our public method. So print numbers. For a, we want to give our private method our a. For num-a, well, we want to print b num-a, so let's give that b. C is the same, and the number of c's we want to print is d. And the so far string that we'll build up with every recursive call is initially empty, so that will be our starting value. So for our base case, if the number of a's in our string is equal to b, or the desired number of a's, and the number of c's is equal to the desired number of d's, we should print the string that we found on a new line. So, well, how do we track the number of b's and the number of d's? Or sorry, the number of a's and the number of c's. We have these num-a and num-c variables with given initial values of b and d. So what do we have to do to update the counts of the number of a's and the number of c's in our string? We saw this in section, but one approach we can do is every time we add an a or a c to our string, we can decrement the number of a's and the number of c's. So you'll start at the initial b and d values and then decrement all the way down to 0. And once the number of a's or number of c's hits 0, we know we've added the desired numbers of a's and c's. So for a number of a's to be equal to the desired number of a's, num-a would have to be equal to 0. And for the number of c's to be equal to the desired number of c's, our num-c would have to be equal to 0. And if this is the case, we just want to print our string on a new line. So we use println in this case. Otherwise, when the number of a's is less than the desired number of a's, and the number of c's is less than the desired number of d's, or the desired number of c's, we will want to make recursive calls. So if num-a is greater than or equal to 0, as there are either 0 or more a's to print, and the num-c is the same case, where we want to print 0 or more c's, we want to make a recursive call. What does this mean? Well, we want to explore all possible options, right? We can either add an A or a C for each recursive call or each choice in our decision tree, if you want to think about them that way. So if we want to add an A digit, for our string, we can make a recursive call where we give it a, decrease 1 from our num a's, because we're adding an a to our string, and then the c and the num c's don't change. And we add an a to our so far. The other choice we can make is to add a c digit to the string we're building up. So the a and num a's don't change, but we added one c to our string. So num c for the next print numbers call will be one less than this call. And we'll append a c to our so far string. And one thing to note, this code handles our implicit base case, where we will stop recursing if we added too many a's or too many c's to our string. Let's run this. Nice. And mark just to make sure. Great, we passed all the tests. Yeah, so this approach of finding a so far and the counts that we care about, finding when the value that will determine whether or not we stop recursing, or if a base case is valid or not, is an approach that can be applied to pretty much every single exhaustive search problem. It's really all about identifying what we're building up, identifying what value will determine when we stop, and how to update and keep track of those values. Other than that, it's the same problem, but painted slightly differently. I hope this helps, and I have one more review video.